So this is kind of the last part of 5.1. And we just have a couple of examples, but there's some really good conversation to have here. So I'm excited to teach this part. And I know you're excited to learn it. I know that's how this goes. Oh, woo! Hallie gave me. All right, example 5. It says state the domain and range. State the domain and range of the following functions. And we get two functions. Function A is going to be f of x equals, parentheses, x minus 2 squared plus 1. And function B is going to be f of x equals negative, open parentheses, x plus 3 squared plus 4. Okay, so two separate functions, two separate parabolas, and we're going to have domain and range for these two functions. So when you start thinking domain and range, I need you to start thinking of your toolkit functions. We talked about domain and range for those toolkit functions. That was the day that y'all were sleepy and I made you go stand over here, and then we went over here, and then we did. Remember all of that? Okay, so for a parabola, for a quadratic function, it looks like this. It's a U-shaped function. It is going to always go forever and ever left and right. There is nothing bounding any of these functions on the right and left side. Okay? So your domain for quadratic functions, no matter what happens to them, the domain is always going to be negative infinity to positive infinity. Because of the nature of the function, the u, it extends to the right and the left forever. Okay? These are continuous functions, meaning there's nothing that causes them to break apart. No dividing by 0, no anything like that. This is continuous forever and ever, left, right. Okay? But your range is going to change depending on the function. So if you look up here at the toolkit function, you'll see that I've graphed it starting with a vertex at 0, 0. Range always measures from bottom to top. So on your toolkit function, the bottommost part is 0, and it's going to go from 0 to infinity on this toolkit function. Right? We know that both of these are parabolas because they both have this squared term. Right? Both are quadratic. But both of them have some parameters that have affected where it's located. Who can remember this form, what it's called? Vertex form. Why do we call it vertex form? Because you can see the vertex, right? So where's the vertex on this parabola that we're talking about for part A? So this vertex is going to be located at, it's not negative 2, insiders lie, 2, positive 1. Right? So if I know that, I know I could plot it, 2, 1, and I need one more piece of information in order to tell its range. I need to know if it's positive or negative. I need to know my A value. And in this case, the A value seems to be 1. There's no number there. It's positive 1, which means this parabola opens up. So you've got a vertex and you've got the direction that it opens. Those two things determine the range. Range always is measured from bottom to top. So what's the bottommost part of this parabola? 1. We call that the minimum value. It's the minimum. So where range is going to go from 1 to what? Infinity. These tails say it goes forever and ever, up and down. Up, not down. Up. Forever and ever up. So from 1 to positive infinity. Are you putting all of that together?
Is it always going to have a bracket?
wherever the maximum is or the minimum value is, it's going to touch there. So square bracket there, parentheses at infinity. Good question. Okay, so let's identify the vertex on letter B. What is my ordered pair for my vertex here? -3, +4. Okay, so if I plot that, that's going to be 1, 2, 3, up 4. And this one opens down like a frown. And you don't have to graph these, okay? When you get into your homework, you're not going to have to graph them. I'm not going to grade whether or not you graphed them. But I think as visual learners, a picture helps. So once you start getting the hang of your vertex, really you're looking at your K value. You're looking at the 4 or the 1. And then you need to know, does it open up or down? And in this case, it opens down like a frown. This is a maximum. Maximum, right? So what's my range? If I'm going from bottom to top, the range is going to be to 4. Okay, so if it's a minimum value, you're going to lead with it. It's going to go minimum to infinity. If it's a maximum value, you're going to end with it. It's going to go negative infinity to maximum. Are we clear on that? Any questions on domain and range? No? All right. Okay, so the common theme that I have when I'm teaching Algebra 2 is, when will I ever use this? I hear it all the time. Mostly because what we're doing in this class is skill work, okay? It's like the off season to athletics. In off season, I go through and I lift weights all the time. Or you do jump rope exercises. Or you do, burpees. But whenever in the middle of a softball game do I drop down and do some burpees in the outfield? It's not going to happen, right? Well, next time you're on the pitcher's mound, I'm going to look for some burpees. Okay? All right, well. Anyways, you don't do those skills during the game, right? But you got to practice those skills in another setting. Well, for me, Algebra 2 is the skill setting. This is when we're building the skills. We're doing drill, skill. And all the time, we're just solving problems, right? We're learning the math. Later on, when you get into pre-calculus, when you get into calculus, and most of all, when you get into physics, we start applying those skills to real-world problems, okay? And so you'll ask the question, when am I ever going to use this? Well, in Algebra 2, it makes very little sense. I'm not going to just whip out a quadratic equation in the middle of the grocery store line, right? It's not going to happen. So it's very hard for me to help this relate to you guys because right now we're not in the game. Right now we're preparing for the game. Does that make sense? Okay, but if you were to take these upper level classes, then you see all of that application coming into play. Most importantly, physics, because I teach physics and I see it all the time. So the question here is, when will I ever use quadratics? Well, have you ever thrown anything? In your life, have you thrown something? Probably, right? And so we call that projectile. A projectile is an object that's either been thrown or launched. And so anytime we're tracking what we call projectile motion, trying to see what's the track of the ball or the rock or the pebble, anytime, or the rocket, okay? Anything that's been launched or thrown. When we start looking at that, we are calling this projectile motion, and it's a parabola. Every time. It's a quadratic function, okay? One question is, why do they always open down? When we're doing projectile motion, why do they always open down? In one word, anybody? Gravity. Gravity. What goes up must come down. Okay, I don't ever throw something that it does this. Just don't see it. So the most practical application of projectile motion or of a quadratic function would be parabola to track a projectile. What does the top tell me, the vertex? How high it went, right? The vertex will answer two questions. It will answer time, and height. Typically, your x value will tell you time, and your y value will tell you height. So this is on an axis where along my x-axis I see time, and along my y-axis I'm seeing height. A lot of times we'll see this as a function, h of t equals, where h would give you height and time is your t value, right? What do you think the y-intercept is right here? This point 0, comma, y. Where it starts. Where it starts. That's typically going to be your starting height. And what do you think we find right here? This x-intercept. Where it lands. Okay, so you could find distance, how far did it go across, where it landed. You could also find, if I'm measuring time for my x-axis, when it lands. When it lands. Are we seeing the application here? Okay. All right, so I'm going to read you a problem. And this problem says, a ball is thrown upward from the top of a 40-foot high building at a speed of 80 feet per second. The ball's height above ground can be modeled by the equation h of t. So this is going to be a height equation. H of t equals negative 16t squared plus 80t plus 40. I'm going to read you the problem again, and you're going to tell me what these numbers mean. A ball is thrown upward from the top of a 40-foot high building. That's your y-intercept. You see it? That's your c value right here. So if we're going to graph this, I'm going to scale it. Start probably at 40. And I'm going to count by 40. So 40, 80, 120, 160, 200, 240. Well, why can't I add 280? 320, 360. I bet that's probably high enough. Okay, so I'm starting down here. This is my y-intercept. Building's 40 feet tall. Thrown at a speed of 80 feet per second. Do you see that? That's right here. 80 feet per second. That's your initial velocity. Those of you that come on into physics later will get that number. They'll tell you initial velocity, and that's where it goes. Okay. And then this negative 16 out in front, that's pretty standard. If we're in units feet per second, then I see a negative 16. If we're in units meters per second, I see a negative 4.9. So what do you think that number, that negative 16, one, it's negative. It's always negative. And two, the number is always 16 on Earth. Could be different if I was on the moon or on Mars. So what do you think that 16 is? Acceleration due to gravity. Okay, so that 16 you're going to see pretty much on all of these problems. As long as your units are in feet per second, that 16 is always going to be there because that's calculating the rate at which it's falling. And that's standard on this planet. Cool? Kind of understand where these numbers are coming from? Okay, so the three questions that they're going to ask us right now are, when does the ball reach the max height? So question A, when does the ball reach max height? So what is it asking for? The vertex. And which part of the vertex? Okay, so let's ask question B. Question B says, what is the maximum height? What is the maximum height? So I'll tell you that both A and B are about the vertex. A is the x, or the t. When does the ball reach max height? So if I'm talking a vertex, x comma h of x, or t comma h of t, the when question is time. This is for t. And the what is the maximum height, or how high did it go, that's your h of t question. Does that make sense? So on your vertex, you're getting two pieces of information. You're getting a time and a height. Time and a height. And you have to know which one answers what question. When does the ball reach max height? We want to use that axis of symmetry to find the time at which this occurs. Okay, so we'll have negative b over 2a. That's going to be negative 80 over 2 times negative 16. Somebody go ahead and compute. Don't get up and get a calculator. Just, you'll be all right. 5 halves or 2.5 seconds. At t equals 2.5 seconds, so I'm going to let this be 1, 2, 3, 4, 5. At t equals 2.5 seconds, so somewhere right in here, the ball reaches a max height. T equals 2.5 seconds. What's the second question here? What is the max height? So how do we find that? We need h of 2.5, right? That's what we're looking for. We're going to plug in that 2.5 for t, and we're going to see how high was it then. H of 2.5. So negative 16 times 2.5 squared plus 80 times 2.5 plus 40. Don't worry, Patrick's got us. No pressure. $140 feet. 140 feet. Last class, they got 340. They were wrong. Y'all are right. 140 feet. That's its max height. So what does that tell me about the vertex? What's my ordered pair for my vertex? So 2.5 comma 140. Feels like this parabola goes up through here and back down. Pretty cool? Okay, what's the next question it's going to ask us? What do you think? If you were thinking about this ball or a rock that had been thrown off the top of the building, what would you ask? When did it hit the ground? X-intercept. When does the ball hit the ground? When does the ball hit the ground? And so that's an x-intercept question because we want to know at what time, t, are we on ground level? How do I find x-intercepts? Set your function equal to 0. So we want to set h of t equal to 0. And we're solving for time where that occurs. Set your h of t function equal to 0. I'm going to go over to the next page for just a second because we're going to have to quadratic formula here, right? If we set h of t equal to 0, that's going to be negative 16t squared plus 80t plus 40 equal to 0, right? This is h of t equal to 0. I'm going to have to use the quadratic equation here because that does not factor. Cool? So who can remember the quadratic equation?
Negative 80 plus or minus the square root of b squared minus 4ac all over t.
Beautiful. Beautiful. So we're going to plug in these numbers, A, B, and C, into that quadratic equation. T equals negative 80 plus or minus the square root of 80 squared minus 4 by negative 16 by 40 all over 2 times negative 16. In my last class, they were making the mistake of bringing that negative 80 to the front. It's all over 2a. Everything's over 2a. So the first thing you should do is open a fraction when you're typing this on your calculator for your own selves and not waiting on Patry to do it for you. Anybody got a number? How many numbers should I have? 2, right? 2 x-intercepts. What are my numbers? No. Tate, you got numbers? Negative 0.458 and 5.458. Okay, so again, this is the application because this is operated perfectly. Okay, we did the quadratic equation. Tate put those numbers in there. He's got 2 perfect x values. But what was the question? When does the ball hit the ground? So what are we finding? What does T stand for? Time. Can time be negative? No. So if you look back at this picture, this makes perfect sense. We know that the ball started at 40 feet in the air. So any time that happens before that doesn't count. So we throw out this negative time. That's pre-throw. Time can't be negative. So unless we're launching from ground level, in which case my parabola is going to start at the origin and go up from there. Okay, it could. But if we're starting from any height on the y-axis, then that time before gets thrown out. We don't use it. Does that make sense? Okay, so the question, when does the ball hit the ground, happens at 5.458 seconds. Okay. T equals negative 0.458. Negative 0.458. And that exists on the graph. You can see it over here. But we threw it out. And if you're looking, this one is the one we found. T equals 5.458 seconds. That's that point right there where it does hit the ground. Okay. All right, I'm going to read you a new problem. You've got about 15 minutes left in class, and I want you to solve it on your own. Are you ready for this? I know you're excited. Huh?
We get out of here at 40.
You got about six minutes. It's going to be great. I thought we got out at 2:50.
Oh, wait, are we going to leave?
Yeah, I know. I didn't put it all together. About 5 minutes, a rock is thrown upward from the top of a 112-foot high cliff. Y'all ready for this? The top of the cliff is 112 feet high, overlooking the ocean at a speed of 96 feet per second. So the rock's height above the ocean can be modeled by the equation h of t. Can y'all tell how fast I'm going? H of t equals negative 16t squared. Again, that's acceleration due to gravity on Earth. It's negative. What goes up must come down. Plus 96t, that's our initial velocity, plus 112 feet above the water. That's the cliff height. 3 questions. When does the rock meet max height? Gosh. When does the rock max out? Question B, how high? How high does it go? So again, just find your vertex. And letter C, when does the rock hit the ocean? When does the rock hit the ocean? And go. When does the rock hit the ocean? So max height, that's going to be the vertex. And your x value tells you when, and your y value tells you how high. Sorry, I forgot. I got a win. Axis of symmetry. T equals negative b over 2a. You got it, Ashley. You're going to be all right. Just break a little bitty sweat, cry just a few tears. It'll be fine. Negative b over 2 times negative 16. I got 3. Agreed? So when does the rock reach max height? That's going to be at t equals 3 seconds. How high does it go? Oh, we've got answers, and I didn't do it. Awesome. So we found h of 3 to be how high? I got 264. I also got 264 feet. 264 feet. So we just plugged in that 3 into our H sentence, and it outputs height. Ah, gotcha. Okay, so our vertex is located at 3, 264. The 3 tells us time. The 264 tells us height. Everybody good with that? Mm-hmm. Are y'all just saying mm-hmm?
Maybe.
When does the rock hit the ocean? 7 seconds. So that's your quadratic equation. Or it could factor, and this one will factor because all 3 of these are divisible by 16. If you pull a negative 16 out, you can factor it. It happens at t equals 7 and at t equals negative 1. Throw out the negative 1. Time's not negative. So when does the rock hit the ocean? At t equals 7 seconds. Cool? Do you really understand?
I do. I just didn't. It was stressing me out.
I know.
Where did you put it on your 64 from?
Plugged in the 3.
Whenever she did the setup.
So we got h of 3, which means I put a 3 here for t and for t. Hey, yes, guys, listen. Stop.